What do you do when you have a pile of text documents and your boss comes to you and says, hey, I want you to extract value. I want you to extract insights out of those text documents. What you do is you reach for the handy dandy k-means clustering algorithm and then combine that with a machine learning predictive model. And I'm going to teach you this powerful technique that I've used over and over again in this video. These techniques work with any textual data. Doesn't matter if it's emails, SMS text messages, if it's Word docs, or if it's notes fields in various IT systems that you might have, whether you work in healthcare or in finance or whatever it might be. So I'm going to use Python and Excel in this video, but it doesn't really matter because the Python code is exactly the same whether you use Python and Excel or use Jupyter Notebooks or use VS Code, whatever it might be. By the way, if you want the PDF of the slides in this video and the Excel workbook, check the description below. So let's get started by talking about how we prepare our textual data for analysis by using the mighty TF-IDF calculation. If you're not familiar with document vectors, check out this video on my channel to learn more. At base, document vectors are essentially the way we take raw textual data and then transform it into a tabular representation that's useful for analytics. And document vectors are super powerful. They're used all the time in all kinds of scenarios, but they do have some limitations. So first up, document structure is not modeled by default. What you typically get is what's known as the bag of words model when you use document vectors for your text analytics. So terms like the United States, which is a collection of words that are very commonly used together, are actually distributed across your table. So for example, the word United might be in column 34 and the word States might be in column 123. So what you lose is that structure. The United States, Great Britain, European Union, those things actually get kind of scattered hither and yon. You can try to add some structure to your document vectors using something called n-grams, and that's essentially combining two words together as a single thing. That's beyond the scope of this video. Feel free to Google it if you want to learn more about n-grams. So you can do that, but it's not nearly as good as the original structure, right? The entire English sentence, for example, has far more structure in it than even what n-grams can provide. So that's one limitation. Another limitation is that these tables, these matrices, tend to be very, very wide. If you think of a column, these types of representations suffer from high dimensionality. It's not uncommon in real-world scenarios for you to have tens of thousands of columns, maybe even hundreds of thousands of columns, depending on the size and complexity of your text documents. So they're very, very wide. And that produces a lot of problems in many, many analytical scenarios. And closely related to this is the idea that most of the cells, so you have a really, really wide table. Maybe you have rows for all your documents. Let's say you have 40,000 columns and you have 10,000 rows because you have 10,000 documents. Most of the cells are zero. They lack any information because most documents don't contain all of the words. So it's very sparsely populated. You see like the word mononucleosis, for example. I used this example in a previous video. Might actually show up as a column, but it's only in one of your documents. So every other row, every other cell except for one is zero. This is what's known as a sparse information problem because zero conveys you no information. So these very large tables are mostly empty. They're mostly devoid of information. Next up, there's this class in scikit-learn that we use called the count vectorizer. It's the most common way in Python to take your textual document and then transform it into this tabular representation. And the problem with the count vectorizer, as awesome as it is that it does not take into account the differences in lengths between documents. And let me give you an example to illustrate this point. So a count vectorizer will produce a table that looks kind of like this, where every row happens to be an individual text document, and then each column happens to be some word or term or token in the document. And what we can see here is that the first document has much higher counts than the other documents. And that's simply just a function of the document being longer. That's a problem in many analytical scenarios. What you would like to do as much as possible is make every document on relatively equal footing so that you can actually say, look, I want to go beyond just the lengths in terms of comparing my documents. I want to get to the spirit. I want to get to the abstract concepts that it talks about. So I need to make sure that a long document and a short document are considered on more equal footing. And that's where the TF-IDF calculation comes into play. So to address some of the limitations that we talked about in the last slide, the term frequency, inverse document frequency, or TF-IDF calculation was created. And TF-IDF is amazing. It's pretty much the de facto standard in text analytics. You almost always use TF-IDF your data as an experiment to see if it actually improves things. It's just the de facto standard. And it is commonly used across many scenarios related to text analytics. And here are some examples. So for example, in the early days, TF-IDF was commonly used in search engines, not so much anymore in the modern age. You can certainly think of search as a text analytics problem, and TF-IDF was certainly useful in the search engine space. Text mining, certainly something that you do. For example, in my next video where I'm going to talk about something called topic modeling, you typically TF-IDF your data before you do the topic modeling. And then, of course, document clustering and classification, which we're going to be looking at in this video. TF-IDF is also extremely useful for that. So you can think of TF-IDF as a transformation that you apply to the document vector matrix. So those counts that we saw on the previous slide actually get transformed due to the TF-IDF calculation. And then what you get back essentially is a new version of that particular table. So you'll have all the same rows and all the same columns, but the actual numbers in the cells will be different because they'll be the result of the TF-IDF calculation. So I am going to go over the math of TF-IDF, but don't panic. It's actually very, very straightforward. So here is the TF-IDF calculation. And what I'm going to do is I'm going to unpack this step by step so that it's not nearly as intimidating. So first up, let's think about what the left side of the equal sign means. So this side over here. So the weight or the value that shows up in the cells after you TF-IDF the original account data. So the weight is a function of a particular term in the vocabulary. So you can think of the little t as being a word. The, United, States, European Union, individual words, that's what T means. And not surprisingly, if T is term, D is document. So what we want to know is for a particular term, for a particular document, what's the weight? What is the value that we stick in a cell? Because if my rows are documents and my columns are terms, the intersection of those two things is this individual cell in my table. So this is the cell value. Now, next up, we have to look at what's to the right of the equal sign. And the first thing that we want to do is take a look at TF, which stands for term frequency, which is pretty self-explanatory, right? Essentially, it's like how often does a particular term show up in a document? Because notice I have my little t and my little d. And then we multiply the term frequency times the inverse document frequency. And we're going to go through the actual calculation for IDF. But right now we want to concentrate on the intuition. And the intuition is that the IDF calculation increases the importance of less frequent terms. That's super important, right? Because if we have a term like mononucleosis, some sort of medical or technology term that shows up maybe in one document or very few documents, if we just use raw counts, it doesn't look like it's all that important to our analytics. So what we want to do is we want to say, look, we want to raise the relative importance of infrequent or rare terms just so we can put things on more equal footing. That's the intuition. So first up, let's go take a look at the term frequency calculation. So here's term frequency, super easy. It is the count of term T in document D over the total number of terms in document D. Pretty self-explanatory, but I will show you a contrived example just to really solidify the idea. So let's say that we have this particular document. What we can do is we can say, look, what is the term frequency of term 1 within this document D? And we say, okay, the count of term 1 is 3, and then there are 3, 4, 6, 9 total terms, goes in the denominator. So the term frequency of term 1 in this particular document is 3 divided by 9, or 0.33333333. Pretty easy, right? Not very difficult at all. What's a little bit more complicated is actually the inverse document frequency calculation, which we're going to cover next. So here is IDF, the inverse document frequency. If you Google this or you go to Wikipedia or something like that, you're going to see multiple definitions in terms of the mathematics of IDF. What you see here is what's offered as part of scikit-learn in a particular class known as the TF-IDF vectorizer. So what we're covering here is actually germane to Python and specifically scikit-learn. Just know that IDF calculations can vary. This is the one that Python uses in scikit-learn. That being said, let's take this apart. So let's start within the parentheses first. Let's ignore this log thing here. So what does N stand for? This little lowercase italicized n here. That is the total count of documents in your corpus. And corpus is just a fancy way of saying the collection of your documents, the stack of your docs. So how many documents do you have total? And then what we do is we say, okay, cool. Let's look up the number of documents containing a specific term T. Because notice that IDF is a function of T, not T and D, as we saw with term frequency. Just the term, United, States, European Union. Those are all individual terms, so we're calculating the IDF per term. So then we say, okay, for a particular term T, let's say European, how many documents actually have it? That's the document frequency. That's what DF means. So let's say that I have 100 documents. This would be 100 if they all contain European. And then all we do is just add these up. So if I have 1,000 documents in my corpus, I get 1,001. If it's 100 here, as I mentioned, it's 1,001 divided by 101. And then we feed that into the logarithm function. And I'm not going to go into logarithms. Don't worry about it. You can totally look that up using NumPy or whatever if you're really, really interested. So then we take the log of that fraction and then add 1 to it. So that's a bit abstract. So let's actually cement what the math is doing intuitively with a hypothetical example. So here's my hypothetical example. I have 100 documents in my corpus, and this hypothetical term 2, is present in 5 of the documents. So all I do is plug and chug. So the IDF of term 2 is the log of 1 plus 100, because I have 100 documents total, goes over here. Term 2 is present in 5 documents, so it goes there. So I go to the log of 16.83 plus 1, and that gives me a final value all the way over here of 3.82. Notice that because of the calculation, its importance gets raised. And what ends up happening is the more common a term is, the lower this number becomes. That kind of makes sense, right? Imagine that you have a stack of magazines. That's your textual documents, and they are some sort of automobile magazine. And in the United States, we typically use the word car very often to describe an automobile. So the word car is probably going to show up in every single one of those magazines, probably multiple times. So that tells you that in general, for this particular collection of documents, that the word car really doesn't have that much information. So you would want its calculation to be actually lower than something rare, like Studebaker, which if you're not familiar is like an old school car. So Studebaker would actually have a higher value. It would be infrequent, so it has more information. So that's how TF-IDF works. So let's run through a complete example now of how we actually can do a full TF-IDF calculation for an individual cell in our document term matrix. So we're going to use a hypothetical example where we have a term T appears in a document D 3 times. Document D has a total of 9 terms, and my corpus has 100 total documents. And then term T is present in 17 of the 100 documents. So it's not super common, but it's not super rare either. So first up, to calculate TF-IDF, we need to start with the TF, the term frequency. The term frequency is the count of the term T in document D divided by the total number of terms in document D. And in this case, we know that term T appears 3 times. So the 3 goes here. We know that document D has 9 terms, which goes here. 3 divided by 9, 0.333333333, so on and so forth. So I got my term frequency here. Next up, I then calculate my IDF. And I just plug and chug. So I have 100 documents, so that goes here for my N, and I have term T present in 17 of the 100, which goes here. So 101 divided by 18 plus 1, this fraction fed into the log first, of course. And then what we can do is run plug and chug. And notice here that the value of this right here turns into this, which turns into this. And notice, like I said on the previous slide, this term shows up in 17 of 100 documents. So notice how this number is lower, which is what we would expect. And then we add 1 to it, and we can see here 2.7247. Now, lastly, what we do is we multiply these two things together, 0.333 times 2.7247, and we get a value of 0.9081 that goes into the cell. And that's how TF-IDF works. So let's go ahead and now go to Excel, and I'll show you the Python code for actually doing all of this, performing a clustering, and then using a predictive model on top of the clustering of your text documents to try and understand what's going on in them. All right, here I am in the workbook file. And once again, if you want the files, check the description below the video. There'll be a link where you can get these. So what I'm using is the same data that I used from the previous video on Naïve-based classification, which is the sarcastic headlines dataset from the Kaggle website. For this particular video, it doesn't really matter what the data is. It's just an interesting data set to play around with. Here are all my text documents right here. This could be emails or SMS text messages or whatever it might be. So this is my raw text data. So let's see the Python code. So what we can see here is I've already got the code put into the workbook. You don't want to watch me type it out. So let's go ahead and take a look at the first thing we're going to do. So the first thing that we're going to do is load up our textual data. So we're going to load up the table from Excel using the Excel function and store it in a pandas data frame, which I'm calling headlines_train. So if I run this, what I'll get is some information in the diagnostics pane. And there you go. You can see here the information in the diagnostics pane. I have 4,005 entries, which means I have 4,005 rows. I got 3 columns, one of which is a label, one of which is my raw textual data, which is what I care about, the headline. And this is just the link to the original article. So I've got my raw data loaded into a data frame. But it's just string data. It's just textual data. There's not much I can do with it right now in terms of analytics. So what I'm going to do is I'm going to transform the data. I'm going to tokenize it. I'm going to break it into individual little words. And then I'm going to apply the TF-IDF calculation to it using a class from scikit-learn. And if you're not familiar, scikit-learn is the primary machine learning library in Python. So let's take a look at that code. So this is the code for actually taking the raw headline textual data and then transforming it into a tabular representation where all of the numbers in the table are TF-IDF calculations. And so we can see here is I'm importing the TF-IDF vectorizer class from scikit-learn. So this class does a lot of cool things for us. It reads in our text, it breaks it up into logical chunks called tokens, and then it performs the TF-IDF calculation around the whole collection of data. And what we can see here is I'm instantiating an instance of the TF-IDF vectorizer class. And notice what I'm doing here. I'm doing something here really, really cool. I'm actually using the built-in functionality for stop word removal. And stop words are very commonly used words in language, but don't actually offer a lot of meaning. The primary example in the English language of a stop word is the word the. So stop word removal says, like, pluck words out like the and is and things like that, and then only leave the other words behind. We then say, okay, cool. Go ahead and fit and transform. So the fit transform method does 2 things. First up, the fit portion of the code says, go through all the data and learn what you need to do. And then once you've learned it, actually transform it. So in this case, go through all of the individual headlines, break them out into tokens, remove the stop words, and then perform the TF-IDF calculation on everything. And then just give me back the net result, which is an object which I'm calling my doc term matrix. And then what I can do here is run this code and get some output regarding the size. And what you can see here is what I talked about before. You have a very wide data frame, many, many columns. As you can see here, I have 9,682 columns. That's a lot. We probably should deal with this. This is probably way too many columns because they're mostly going to be 0. So what we can do is actually add another parameter to our TF-IDF vectorizer to actually say, look, only include the terms, only put columns into my document term matrix, into my table, if the term actually shows up in a minimum number of documents. So let's see what that looks like. So this code is basically the same as what we saw before, but I've added this thing known as the min document frequency parameter. And what this says is, look, you only keep columns in the final table if the term shows up in at least 5 documents. If it shows up in 5 or more, keep it. Otherwise, kick it out. And if I run this code, which has now been highlighted with IntelliSense, yay. If I run this, what we can see now is that, sure enough, I get 1,271 columns. So I get a radical reduction in my columns here. So we're going to actually use this version of our table, of our documents and our terms, with our clustering. So moving on, I'm going to go ahead and use k-means to cluster my documents. Because if I have a pile of documents, I don't know anything about them. And I certainly don't want to read them one by one to try and figure out what they contain. So I can use the computer to help me out. So k-means is a clustering algorithm. And by the way, if you want to learn more about k-means, check the description below the video here. I've got a link to a crash course on k-means that you can take for free if you want to know more about k-means. And k-means will try and group the documents for you. Now, there's a couple things you need to know about k-means. First up, you have to tell k-means how many clusters are you going to find. And in this particular video, I just arbitrarily picked 3 clusters. There's actually a technique that you can use with k-means to try and figure out, try and dial in how many clusters you need. That's known as the elbow method. So you can go ahead and just Google k-means elbow method, and you get a lot of information about it. So we're going to go ahead and try and find 3 clusters. And then what I do is I invoke fit on my k-means object, and that says go learn, go find the clusters. So if I run this code by hitting Control Enter, it comes back lickety split. It doesn't take long at all. Now here's the problem. When you have a big pile of documents and you cluster them, you have no way of knowing right off the bat what kind of documents are in cluster 1 versus cluster 2 versus cluster 3. You actually have to go figure that out. The clustering algorithm doesn't tell you that. In my next video, we'll talk about topic modeling, which is kind of an interesting way of actually trying to figure that out automatically. But when you're doing clustering like this, you don't know. You just have documents in various clusters. So one way you can accelerate the process for understanding what's going on in your clusters is to use a machine learning predictive model. So let me show you what I mean. In this particular cell, I am training what is known as a decision tree classifier, which is a particular type of machine learning model. And what I wanted to do is learn how to try and predict the cluster labels, 0, 1, or 2, because remember I had 3 clusters, 0, 1, or 2. Try and predict accurately, document by document, which of the features actually placed each document in one of the 3 clusters. And you can see here, I'm just setting up a decision tree object here that's of the type decision tree classifier. And what I've done here is just pick 100 min samples per leaf just to build the tree. Now, this is what's known as tuning the tree. Don't have time to go into that in this video. If you're interested in learning how to tune decision trees, which is probably a good idea if you're interested in using this technique, there's a crash course link in the description below this video, and you can go ahead and learn how to do some tuning. Next up, I say, okay, cool. Hey, Mr. Decision Tree, go ahead and fit yourself to the data. Go ahead and learn the patterns in the data. And here are the TF-IDF values. Here are the cluster assignments, the k-means labels. Try and learn how to predict the k-means labels from the TF-IDF values. So we're going to go ahead and run that, and we get back a decision tree classifier. And then lastly, what we can do, which is super useful, is visualize the tree. Now, here's the thing you have to remember. The tree is not going to tell you specifically cluster 1 is about HR, and cluster 2 is about finance, and cluster 3 is about logistics. It won't tell you that. What it does is provide you some guidance for how you can more quickly explore the clusters to understand what kind of documents are in each cluster. So let me go ahead and run this code here, which visualizes the tree. I'm using the plot tree function from scikit-learn. I pass it in my decision tree model, my predictive model. Notice what I'm doing here is I'm getting my feature names from my TF-IDF vectorizer. So this is actually the list of the individual columns, the words. So for example, United, States, European Union, so on and so forth. And that just allows us to actually look at the visualization of the tree and understand which of the columns, which of the terms, which of the words the decision tree found was predictive of the cluster label. So I'm going to go ahead and run this, and this will produce a pretty good sized visualization. So I'm going to go ahead and collapse the old formula bar, right click on my picture in the cell, create a reference. And what we can see here is the visualization. Let me just shrink this a little bit so we can see the whole thing. Now, like I said, this isn't going to tell you definitively what is in each cluster. But what it's going to do is help guide you for the kinds of things that you should be looking for. So notice that first up at the very top of the tree, the token, the word man, was found to be most important. It was the highest thing. So essentially what you can do is you can say, oh, okay, the word man was very, very useful in predicting cluster assignments here. And then what we can see over here on the left side here is the word new was also pretty important, and then Trump. This can help guide you to start understanding how you would actually analyze your data. And then over here we can see man once again. And notice what we're talking about here is man vis-a-vis its TF-IDF score. This is a very, very simple and contrived example. What I'm trying to do is illustrate the concept of what you would do. You would obviously use a more complicated and tuned tree to understand what's going on. So for example, you might say, okay, what I will do is Trump, for whatever reason, is super important in terms of the classification. Maybe what I will do is peel off my documents that contain Trump and then start looking at what are some of the other terms that are very, very common in there. In my next video, topic modeling would be super useful. You'd peel off your Trump documents and do topic modeling on top of the Trump documents and be like, oh, okay, well, this is what they're talking about in general. So stay tuned for that video. But this is what I do when I'm handed a pile of textual documents and I have no idea what's going on. I TF-IDF them, I cluster them, I use a predictive model to help start guiding my analyses, and then I start spelunking into the various documents and the clusters based on what the model shows me. Combining k-means clustering and machine learning predictive models is just the tip of the iceberg of what you can do with Python and Excel to extract value out of your text data. As I mentioned a couple times before, my next video is going to be all about topic modeling, which is a super useful technique that automates this idea of going through all of your documents and then finding clusters of words that seem to convey the main subjects, the main ideas, the main topics of what's going on in your textual documents. Super, super useful. I think you'll love it. And when that video is ready, it'll show up on the screen as a tile and you can click it and watch it. In the meantime, what I will do is put up one of my other videos on text analytics with Python and Excel, just in case you will find that interesting. So until next time, please stay healthy, and I wish you very happy data sleuthing.